Hello everybody. And my presentation was made in Windows, so now I'm using Mac, so I think it will be better, right? So, the title of this presentation is Who is the Client? And first, I'm not the client, but my name is Marcelo, and I come from Brazil, the hotter part of Brazil, the north. So I came here with my family 8 months ago, and now it's our first winter, so we are freezing. And oh, Mac, help me. Oh, I should use this guy here. All right. So my presentation it will be short, but I want to tell you about the browser and rendering engine and web developer tools. And the both subjects is included inside the browser. So I'm front-end developer, as I said before, since 2006. 2006 my first son was born, so after that I started to study about HTML, CSS, JavaScript, and making kids. So now I have 3 of them, and a good experience in this subject. So I really like to read about the browser, and I want to go deep inside this subject today with you. So the browser can be, when I say the browser, I'm talking about the most part of browsers, like Chrome, Safari, and Internet Explorer, and Firefox, and so on. Every browser looks like the same inside. They have almost the same structure, and as you can see, the browser can be split in some components. These components, like user interface, is the Chrome part of the browser. Like you have the input to put your address, and you have the history and the part that user can interact with. So I want to focus on this component here. In some cases, WebKit or Blink or I forget the other name. So yeah, I want to focus here on the render engine and its job, what it does. So the render engine for us, I will say for us because I'm front-end developer. I don't know if there is many front-end developers here. Who is front-end developer can say to me. Okay, it will be good for you. For others, I hope so. I don't know. And so the render engine is the most important for us, component for us, because it makes it helps us to give some answers for the user. As you can see here, we have the critical rendering path. This critical rendering path is the process that the browser will pass through from the HTML part and CSS until to show something to the users. I'm left, so it's good. Yeah. Okay, so as a front-end developers, we are good here in this part and how to make good web HTML code, clean, and so on. And we are good here and to create some CSS styles. But the other part of the job, I forgot JavaScript also here. So the other part is the browser responsibility from the render engine component. So I would say to you that when we send our HTML text suite to the browser and CSS, the browser will start a huge process of rendering. So it will get our HTML on big string. It will parse it to the DOM, document object model as a tree structure, and this process here itself can be already one talk about it because it's not easy. It's this part is not easy because if every time when you create your text, the browser will realize that no, it's not clear, I will fix it to you. Even if you send only one string there, the browser will build it and include your string inside of one DOM constructor. So I would say to you that everybody, not everybody, but most part of people, when we say this expression here, DOM, document object model, we have in our mind that it's not fast. It's the problem. The DOM is slow. The DOM is the font of every problem of the rendering. But I would say to you that it's not. The DOM is it's fast because it's just one object inside of the browser. Hello, hello, hello. Hello. I said boy in Portuguese. Okay. So I would say to you that document object model is not our problem. Our big problem is the other part, the rendering part. When you send your HTML to the DOM, the browser can build this object model very fast. And after that, we discover some CSS file. It will be parsed also. Some JavaScript. Maybe the JavaScript can produce some changes here or some changes here. And after that, the browser will get both document object model and CSS object model. Will match our selectors and the HTML tag, and will build another tree. Inside the browser, we have like one forest. We have many trees, and the render tree is the most important thing for us, front-end developers. Because here we have every nodes that the browser will send to the final user. I would say to you that if you build a lot of things here in the document object model and you set as display none using your CSS, it will be not present here, and the browser will not show it to the user. So this I can scream also, no problem. Nema problema. Hello. Yeah, I already know Polish. Okay, let me remind. Yeah, okay. Can you use both? No. Let me remind you again. Okay, I was here in the render tree. So this, I know that it looks like boring, but it should be more clear when you see it how it happens inside of the web developer tools. It's good. It's very, very nice. I can spend like hours just look at the web developer tool. So I would say to you that I'm speaking too loud or no? Hello. Okay. And render tree is we need to focus on render tree because everything that we have inside here, every node that we have here, will be shown to the user. And what you don't have here, it needs to be built again. For example, I would say that if you have, we have many cases that we have one submenu, for example, and it set like display none, so it's not presented here. So every time when the people click in one button on the website, no, I will cry. Hey, you are playing to me. I know you are playing with me. Let's back to remind again. Okay, I was talking about if you have a huge drone, oh no. If you have a huge items here, like hidden by display none, you will not have it here on render tree, and as a consequence, the user are not see nothing there. And when you click in the button and you change the properties here, using JavaScript, for example, if you set an event, when I click into the download, I will change the CSS property to from display none to display block, for example. It will be included here on the render tree, and we have a huge process for rendering. So this is our problem, and I want to tell you how you can see it in the browser, how it works. So let's move on. I want to show you about DOM. Yeah. Okay, this is how the DOM looks like. You have the tree extractor. As I said before, this is fun. Please take a look here because we will set it like display none after that. It can be one entire document. It can be whatever, a huge part. So, as I said before, this is not our problem. I will come back here because I want to answer one question that is in our website, in my presentation. You can ask me that if
you don't have to use it. I think
okay, no problem. What happened? Let's pray. I'm afraid. Okay, as you see, it's already rendered. Where is my let me just 2 seconds, right? I need to make it first. Yeah. Yeah, why close? Is it no? Come on, from here. Why am I talking? Yeah, this one. No, please, click to come here to open again. Maybe well, it's closed. Yeah, it's closed. No. Okay. Let me present again. Okay, guys, my name is. Now I get lost. Yeah, I was here.
Next slide. You were on next slide.
Next slide?
Yes.
Yeah, no, yeah, I want to tell you something about the DOM and JavaScript. Because I said before that the document object model is not our problem. Our problem, I mean, performance problem for now. Because when you change something here, it's really fast. It's like one JavaScript object and with tree structure. Okay, but you can ask me, maybe somebody will ask after that, why we need something like virtual DOM to improve the performance, or why everybody say that, oh, the DOM is so slowly, if I have a huge amount of tags, it will be slow to my client. Because of the render part, not this one. And how the virtual DOM can help me, how the virtual DOM can solve some problems in my performance issues. I would say to you that the virtual DOM is running here inside of the JavaScript component in V8 in Chrome case. So when I would say that every time when you change something here, it's like to press a start button on browser, and it's automatically running the render part. So if you change like 5 items here, and if you run this changing many times, the browser will start this whole process many times. So you will have a problem, a recursion problem in your rendering. So if you put your one representation of the DOM here on JavaScript, and every time when you change here, nothing happened there. Even only when you send some updates for the DOM, it starts automatically. So when you have your physical DOM running here, and you change like 10 icons, the React, for example, or Vue.js, you have one algorithm to figure out the better way to send one update in one time to the DOM, and the browser will render the rest. So this is why, even though you are using virtual DOM, you still have this problem to solve. You still have this rendering part to optimize after that. So yeah, this is how the document object model looks like, and we have the CSS object model also, and you can see that I'm putting one display on this span, and now the browser will make the match between both trees out on the top, and will create this part for us without this span that I would set it like display on. And still, this render tree sometimes looks like the same with the DOM, but it's not the same because we are missing some head part because it will be not printed, as you can see. The displayed on tags nodes are not here, and you can put some other components from the CSS part. If you use like pseudo selectors like after or before, and you set content to it, it will be included here on render tree, not here in DOM part. So the render tree is very nice. And after that, after you have your render tree already done, the browser will move on to the next step. I know it's this is the part. This part is the layout part. This part we have no pixels, still no pixels. The users can see nothing, still nothing. But the browser are doing our blueprint, are putting some dimensions and make a lot of calculations there. This is our problem. And you can solve or optimize it using CSS the most part of the time. And yeah, this is very expensive part. And the worst part happens when you resize our, for example, if you resize the body, if you resize the browser, the width of the browser, the browser will calculate everything again, the layout. So it's very expensive. It will be, it will generate a lot of painting and so on. Yeah, after the layout part, now we have pixels. Now the users can see pixels. So I'm very sad when somebody say that, oh, my problem with my website or my system is because the DOM is slow. Yeah, so it's personal. I don't like this kind of people. So let's move on to examples. I want to show to you this website. When I arrived here in Poland, is my best friend. I have everything here. I cannot. Doesn't matter. Okay, so let me put it here. No. What are you? Oh, no. Okay. Oh, it's here. Okay. Okay, hello, sorry. I would say that I think you can see the whole process that I said to you before, the rendering process here on this tab that you see before. Even if you click here, yes, I like to enable this part, screenshot. Now the website is reloading, and we have a lot of information here. And I want to show you some part. This is a timeline, okay? From start until the end. So this first part, we have here the call tree. The call tree is the sequence of how many jobs the browser does for you when you reload the page. As you can see, the parse HTML, but it's not only the parse HTML. We have here another parse because let me group in here by category, loading part, parse HTML. Yeah, here you can realize that, okay, what the browser does when I reload the website. The browser made the parse of HTML. As you can see, this website is huge. We have a lot of web tags. We have a lot of tags, and it took like 0.3 milliseconds to be parsed to the DOM. And here we have the parse of the style sheets and the evaluate script here and so on. You can see the history of your work here, and the rendering part also, the layout part, the update, the layer 3. Update layer 3 is when the browser make the match of the DOM with the CSS. Okay, so if you want to improve the load process of your website, you can use this tool using the reload part. But I really like this button here because you can focus on one specific part of your website. For example, if you want to know the submenu that I tell you before, and if you want to see if it's fast or no, you can start recording and click there. I'll close again, and I need to come back. And stop. Yeah, so now we are focused on one action, right? So you can see the exact moment when your click happens. As you see, we have colors to represent our actions, and the yellow part is JavaScript. Yeah. Okay, this yellow part is JavaScript. Here we have my event click that I click on the button to show the submenu, and here probably I don't remember when you click there it is changing the submenu from display none to display block. So it will be included to the render tree after that. As you can see, recalculated style. The recalculated style is when you get the CSS object model and match with the DOM. And after that, the browser will move on to the another steps, and that is layout and rendering and update the layer 3 again. This process is cycle. It never stops. Every time when you clicking somewhere or you make some change in the DOM, it's automatically start again. So you can use this tool to see what happened. I don't know if this version of Google Chrome we have, let me see, Ctrl-Shift-P. Common? Yeah. Okay. Painting. Let me see, application. No, we have not. No, that's that. Layers. Yeah, you can see the layers. Yeah, you can see the layers that the browser have made the composition of our layers, and you can see how it looks like and how many layers we have in this website. You can see everything that the browser does for you after that. I think I would show just this basic stuff for you, and from now you can make your research and learn more about it. But it's very, very important for us as front end. Look to the performance on the web developer tools to realize what happened, what the most expensive part for us. Because when you click the button and if you are not going there, if you click the button and you see something is low in your page, you cannot figure out what happened if the problem is in your script or your rendering or your layout part of your painting, and using it's very helpful for us. So I had another example, but it's in my another notebook, and I cannot show to you now. But it's the most important part is this one, and I would say that performance is one feature. It's not a unit test. I saw this phrase. It was said for Paul Lewis. You can research about this guy. He talks a lot about performance, and performance is something that we need to take care. And there is the unique way to see how it looks like and how is your performance, where is your issues, is knowing how the browser works. So I want to stop here. It should be very short, this presentation. So if you have any questions, I'm here. Any questions?
Thank you.
I'll be glad. Thank you.
Why Alex?
Oh, I should have moved. No. Okay. Let me get out from my account.
So no questions, yeah?
Okay. So it's really not for me.
So now we have the last presentation, and after that short about maybe 20 minutes game related to CSS selectors. As Andrew and you already mentioned, it's a multiplayer game for developers. Can I ask a question? Yeah. Question to Marcela? Yeah. Marcela, hello.
Yeah, one question. In that
rendering critical path. What is the difference between adding and removing the DOM element and using the CSS display node, display dot because the second is faster. So which what is different?
Oh, about display none and display block. For example, if you set display none, it will be not included in render tree. But if you hidden a content using like visibility hidden, it will be included. The browser will give layout for this element, and it will be already there. So it will be so much faster. It will be it will be faster. You know. I saw the Yahoo website is using this approach, and yeah,
but
this is a difference.
Still faster than removing comment from the DOM.
Yeah, it's faster.
There is special, I don't know, when it's the piece in the critical functors rendering path.
Oh, let me understand.
Yeah. So basically, I can imagine that display changing the displays of the element also goes through this rendering path. And adding node to the HTML and removing also goes to the same path.
Yes.
But there has somewhat that has to be different because CSS is much faster than adding or removing.
In the end, doesn't matter if you are using CSS to put display none or if you are using JavaScript, for example, to set as display none. Because in the end, the browser will build it as a style sheet parcel also, even though you are using JavaScript. And yeah, so the difference is if you are setting display none, it will be not there. There is no layout, there is no composition, there is no layers. So if you are using visibility, for example, or set top -100 to put outside of your screen, of your whatever, it will be already there. The browser just needs to make some changes in composition layers or something else. It will be faster. Yeah. Thank you. Some more questions or no? No, it's not. No.
Okay, fine. Do I really need the microphone, or can you hear me like that?
It's broadcast.
No, it's not. No, I mean, is it okay? Okay, that's okay. I'll speak into this thing then. Okay, so as you might have seen from the agenda for this meetup, my original talk was supposed to be about modules and scope encoding. Then I sent my slides to Dima. He said it was too simple, too easy. Everyone knows that, so I had to come up with something different. And I like functional programming, so there you go, modules. Well, who am I actually? Well, I'm just some dude. My name is Alex, and just like Kirill and Dre over here, I'm a proud member of 2123, where we do, well, those games for geeks you've been hearing about the entire evening. And I also happen to work for Weeks.com Germany. Well, these guys pay me money, these guys so far not, but who knows. Okay, so I'll be talking about the buffet of monads, and that's the example of what a buffet is. Basically, it's lots of food where you just come in and help yourself to anything you want. And I'm kind of been trying to bring this analogy over to types that you use for programming. So functional programming, right? It's been a real hype recently, like recent 20 years, and everyone's talking about functional programming and monads, and I bet you've seen 1 or 2 monad tutorials on the internet. So we'll start slow and walk towards monads and a bit beyond. Because functional programming is not only about monads, of course, it's just one of the concepts. Anyway, you know pure functions. Pure functions are fun, right? They're easily testable, they return predictable results, and you can easily compose them. So you can have a function from type A to type B, and a function from type B to type C. You can just compose them and get a function from type A to type C. And it's really simple to write your programs with pure functions. You can just compose them as long as their types match. You know, the type of the argument matches the return type. So, for instance, you have your main function, which is a composition of 3 functions, and then this function in the middle from B to C, the f2 function, is in turn a composition of 2 more functions, which you abstracted away in a module. And one of those functions uses library functions, and is a composition of 3 more functions. As long as types align, you can compose whatever you want, and you can move functions around, which makes refactoring a breeze. As long as you match type signatures, you can easily take any function out, replace it with a matching function, and your code will still compile. On a side note, never use Keynote for presentations, because it will do this to your slides. But of course, we can't just compose stuff when it comes to well, you know, real programs, because normally, okay, you have functions with simple values, but what if types are not that simple? What if the value can sometimes not be there? For instance, it can be null or undefined in JavaScript, or you get not a single value, but a collection of values, or even a promise of value, or a reactive stream of values, right? That just keep coming. And sometimes, very often, actually you get values with side effects, which break the purity of your functions. By side effects, I mean they change the environment, or they come from an environment that cannot be reproduced by other functions. So you no longer can do this. You can't just take the function out and replace it with a function of the same signature, because the side effects will be different, right? So all that you can see in a real program. So how do you compose functions that deal with those types? How do you even start thinking about that? And the answer comes from math, really. A bit of mathematical approach wouldn't hurt any programmer, but I really tried to reduce the math in this presentation, so it doesn't bother you, because I'm not a mathematician, so anyway. So suppose you have 2 types, int and bool, and there is a mapping between them, which is just a function that checks if a number is an odd number, right? So you can go from any int to any bool using this function. And if you look at types closely, you realize they're just sets. So int, a type, it's a set that represents all integer numbers, right? Positive, negative, and positive. And bool is a small set of just 2 values, false and true. And this is a function just, well, it's just a mapping between the sets. So, okay, if I want to create a new type, which is called the nullable type in some languages, that is a type that supports numbers or, well, values that might not be there. What do? I just take my set of int and I extend it by, well, just adding one element, which is null. If you use, well, JavaScript terminology, so it's my type, all the numbers there, and null. So I get this nullable int type, which I marked with a question mark. And we can apply the same transformation on the bool type, right? Same set operation, set union. We just add null, and we get nullable bool. But okay, so now we have two brand new types, and we still want to check if this nullable int is odd or not using this function. So how do we write this function f over there? We just check if we have a null, then it's null, because we can't check if null is odd or not, right? Or else, we just apply the function f from here, thus reusing it. That's an example of how it might look in JavaScript, right? So we just use some mapping. So I would say that I'm applying some function to the original function here. Let's call this function map, and that's the definition of this function. So okay, I'm taking a function f, and then I'm returning a new function, which I intend to use with my nullable types. And this function will accept the value of x, which might or might not be null, right? And then if x is null, I return a null. Otherwise, I just apply the function that's sitting comfortably in my closure. And yeah, there it is. I can apply this function to any type, to any kind of function, if it works or with any kind of types, right? It can be a function from int to bool, from bool to int, from int to string, and so on and so forth. I can kind of move this function over to the land of nullable types, right? So my new function is just map applied to the original function. So we can make arbitrary nullable types this way from any type, right? We just need to take the type and attach the null element to it. This transformation in the Haskell programming language is called maybe. In other programming languages like Scala or Rust, it's called option. And it's kind of a function on types. It takes a type, it returns a new type. It takes in an int, it returns a maybe int, a new type, right? So that's how it works with our nullables. And okay, we transform the types, but we also want to preserve the operations on the original types, right? So how do we do this is-odd for nullables? We just apply map for maybe to is-odd. And we can still use the original function. And that's kind of the whole idea that we get types using functions, right? Because maybe the function on types. And we get new functions on those new types automatically based on the existing functions. So we don't have to write new code. We don't ever have to check for nulls. We don't ever have to write those if statements. It's all included in this map function. So we can get new functions for free. And that's a very powerful idea. So maybe this transformation is called the Functor in category theory, and well, it's just a name, and it's usually depicted with this diagram here, which is called the commutativity diagram. And you can see that whichever way you go, if you start from int, and if you take the orange way, right, first you get the new type called maybe int, this nullable type, and then if you apply the f prime function to a maybe int, you get maybe bool, right? If you start again with int and take the green way now, and first you apply the original function is-odd, you will get the bool, and then you apply the maybe transformation to bool, and you get maybe bool. So those two paths are equal. So for types, for transformations that can do that to types and that this to function, we use the name Functor. So maybe is a Functor. That's a bit more abstract. So there is some Functor f here, right? And we just get new types by applying the Functor to objects and to functions between them. So yeah, once again, Functor transforms both types on type level and functions on value level between the values of those types. And yeah, so you can say that a functor is defined by the transformation f of whatever it does with types and its map function. So for maybe this map function was like as you saw here, right? This one. Let me show you another example of a functor. It's a very well-known functor. You used its map function times and times again. It's a list or array functor. And you can see that the diagram is exactly the same as for maybe. You have a type, let's say it's int, and you apply the array of type function to it, and you get the array of A. And if you have function f between A and B, you can map between arrays of A to arrays of B as well. And you know how to do it. You apply this function to every element. And this function is actually called map in JavaScript and other programming languages. So yeah, well, you can see functors as generalization of this idea. Now, you can go even further and compose functors. That is, you can just keep applying them to new types. And that's kind of your buffet. You get types, and there is no end to those types. You keep generating those types based on simple values. So let's see if we go from A and apply maybe, we'll get maybe A. So it's either A or null, right? And if we apply array to that, we get an array of those optional values. And we can do the same with B. And the beautiful thing is that once we define f, we can reuse it again and again. So we can map between maybes, right? But just applying map for maybe to f. And then if we apply to that function here, map for array, we'll get a new function that works with arrays of optional values. So what it does, right? It takes every element of the array, right? Then checks if it's null or not. If it's null, it returns null. If not, it returns the function f applied to it. So you're still reusing the same function, right? That's usually defined in the library level. You have those functors. You just use them as third-party code. What if we reverse the order? It's just the same, but in a different order. First we have arrays of A, and then we have optional arrays of A, right? So the array, we can have either an array of, let's say, int, or we have null. And by rearranging the map functions here, in this composition here, we just get the function that works in those types automatically. So we can both type level operations, functors, so functor f and g, we can compose them and just apply them to types twice. And to mirror that on value level, we also compose map functions in the same order, and then apply them to function f. And f is always reuse. So here's your code reuse. You'll never write the same code again. Yeah, that's kind of the point of functors. You write simple functions. They're pure functions working on simple types. And then you kind of just move, or the right term would be lift them into interesting functors. But so far, we've only seen two functors. The good thing is that you can actually make those functors too. Promises and strings and even input-output with a certain degree of fantasy. And you can define map, the map function for them. And the result would be that you would be able, for instance, to have this add function over there that just adds two numbers. But then this add can be reused in the context of all those functors, so you'll be able to add maybes together, like optional values, and get an optional value as a result. You would be able to add arrays together and get an array of sums, and then you would be able to add values that are not even here, and you would get a promise of a sum as a result, and so on and so forth. But how? That's a bit problematic, but let's first see that we can still combine functors and get interesting types, like this one here. We can have a promise of a list or array of maybe A. So eventually we'll get an array, and this array will consist of optional values, which may or may not be there. And we can work with this type by just mapping first into promise, then into array, and then into maybe. And we're not really interested about how we are getting inside. Okay, so that was functors. Now, we often use functions. Okay, so that's the original function that we use. For instance, our is_odd function from a simple type to a simple type. And then we can move it to a function within a functor, right? So it can be a function from maybe int to maybe bool. But we often have this kind of functions that starts with a primitive type, and then, hello, we moved into the functor type somehow. For example, you have -get, right? That reads a property of an object, and you pass it a string, and it returns you the value of some type, value, right? Or not, or it returns you undefined. So it can be encoded with this maybe type. And then fetch, you pass it to URL, and then it returns you a promise. And then eventually you get responsive tag response. And now factors, when you factorize a number, right? For instance, 24, factors of 24 are 12, 4, 3, 2, and 6. You start with one number, and you get a whole array of numbers. So all these functions move from a simple type to some other type in a functor. And then it's tricky to compose those functions, although you really want to, because you want to still write, purely functional programs. So how do you compose that with that? Because FB is not obviously the same as B, right? So how do you bring these arrows together, this F1 and F2? Here's how. You have your function from A to FB, right? And then F is some functor. That means that B can be moved in this functor, right? By applying this functor to B, you get the F of B. So we just put our function F2 over there, just align them like this, and you have a function from B to FC. And we want to really compose this bit here somehow, right? Then, okay, so F is a functor, and we can apply it multiple times, right? Well, just show that by composing different functors, but it doesn't necessarily have to be different functors. It can be the same functor all over again. So, okay, we applied it here once, and then we apply it to FC, and we get our diagram again, right? But then the functor is applied twice to C. So, for instance, for maybe, that would be maybe int. That means that you unwrap it once, it's either null or maybe of int. If you unwrap it twice, you get either null or int. So that's a bit problematic, because we just want to compose those functions, and the resulting function should be a function from A to FC, not F of C. Who wants an F of C, right? So what do you do? Actually, some of the functors you can just join like that. You apply some operation called, join, and you just reduce the number of functors applied. So functor applied twice to a type is the same as functor applied once. And actually, we call those functors monads. So here, if we add join, just over there, from FFC to FC, right, reducing the nestedness, we can now see a path from A to FC, which is just what we wanted when we wanted to compose A to FB and B to FC. So what we do, we just we start with an A, we apply F1, we get F of B, then we can use our F2, just mapping it into a functor, and we get F of FC here in the corner, and then we get this, we just engage this mysterious join operation and reduce nestless, and we're back into FC, which is just what we wanted. So F, again, those functors that can do that have join defined for them, are monads. And that's basically what monad is. I mean, there is a more rigorous mathematical definition, but who needs that again? Well, mathematicians actually. But so now we have the concept of monad that can just squish functors, right? But join, you can define join for various functors, but and then you can compose functions that go from simple types to functors, right? Like here. But often you want this function to be anonymous. You don't have it right away, this F1. You don't want to give names to anything. So you just use monads in a slightly different form. You use the bind function that goes from FB. So you already have the result of the previous function. You already have the return type F1, and you just then apply a function from B to FC to FB, and you get FC. So you go kind of directly from FB to FC. So that's how the signatures of those functions look like. So F join just reduces nestedness, and bind takes some functor with type A inside, and then the next function that you kind of want to attach or chain to it, and then it reduces to just FB. And then the bind, what it does, what it's supposed to do, it just does the joining inside, so you don't see the nasty nestedness. In addition to that, we also need a function called, usually pure, or return in Haskell, which is very confusing, which just goes from simple type to type rectangle functor. And that's this function here, for example. Okay, so that might be a bit tricky to get the hang of from the first, our site. But I have a few examples that might help you to get this across. For instance, how bind, so arrays are monads. And bind for arrays is defined in very simple terms. But let's check all of them again. So we have pure, which is supposed to construct arrays out of simple values. It just creates an array of a single element. And you have, for instance, you have an int, and then you have an array of ints of this one element. Map is just map from array prototype, right? And then bind is a flat map from Lodash. It has different names, this function. You have an array of arrays, right? Arrays are functor, it's applied twice, it's array of arrays, but everyone here knows how to get an array out of array of arrays. You just flatten them, right? You just concatenate whatever arrays are inside one array, and you get one-dimensional array. So that's the array moment. Then maybe is defined. If we just consider a bit a different kind of definition. So basically, maybe is nothing, which is null or undefined in JavaScript, or just some value of type A, right? So that's maybe for some type A. And then, when we want to map some function over maybe, we have to consider two cases. When we have just some value there, then we can just wrap it again in just and apply a function to the value inside. And if we have nothing, because that's the only other alternative, we don't even care what function is here, and we don't really care to even call nothing by its name. We can just simply return nothing. And bind is also pretty simple. So if you just have a look at the signature, bind, you just go from you handle the case with just, and some function that is supposed to produce another maybe. You see this function from A to FB there. F is maybe. So we just apply this function to the contents of maybe, which is x. So k applied to x will give us another maybe value. And the nothing case is still just nothing. We can't do anything with nothing. And pure, we just go from a simple value to maybe, but just wrapping it into just. So that's pretty much it. If we go to a bit more interesting example, we can consider lazy evaluation, right? That we can have functions that don't return their values immediately, but you have to ask them later, you know, about it. That, okay, now give me the value that you stored, right? Or now do this computation, but just not now. So if we model them in JavaScript with just functions, or you can see it here. So it says, okay, give me an A, and then we will return a function that returns this A. This way we can delay the evaluation of A, right? So we'll have to evaluate this function, we'll have to apply it to get the A out. Like by applying this eval function here. You see, it accepts the function created with lazy pure, it just evaluates it and gets the value outside. Lazy map is actually just compose, functional composition. That's a bit tricky to explain, but just believe me, it's really straightforward to go from a value that is not a lazily evaluated value to lazily evaluated value, and you can still map functions. For instance, you can add numbers. That means you can also add lazy numbers that are not here yet. Let's see the moment. So, okay, we have a lazy of A, right? And then we have a function from some A to lazy of B. So we have basically a function that wraps some value, right, waiting for us to evaluate it. Then we have a function that we just want to apply to the value inside. So what we do, we just create another function. That's the result of bind, because we still want to return a lazy of B. So this new function is our lazy of B. Now to get B, we first evaluate our A. So lazy eval of LA gets us A, right? And now we can pass it into function, because this function works with A, right? It can't work with lazy of A. So we got A out. We apply this function, we got lazy of B. And that's what we wanted to get with our bind. Now with bind, we can compose functions that have lazy results. So we can have multiple functions that return values that are not here yet. And that's actually how you do input-output and computations with side effects. And like that's all the magic. Like how do you do input-output and computations with side effects in a purely functional language without breaking the purity, without making functions impure? You just don't do them. You just use lazy to defer the effects, and then when your program is run, the effects take place. So, but let's get this all like slide by slide. So you got those effectful computations, for instance, print prints some string, and it returns the IO, and those brackets there, they mean the unit type, the just type with one value. And read just returns some string, right, wrapped in IO, because it has side effects. So it's all wrapped in IO. And random, it returns you an int. So, okay, if you just equate IO to lazy, for instance, read will eventually give you a string that user types into the terminal, and random will eventually give you int that the random number generator generates, then you can still work with those values without side effects, right? You can use this, and before they evaluate it, they won't produce any side effects. And the good thing is that we've defined, we made our lazy a functor and the monad. So by doing that, now we can map functions over lazy values without evaluating the lazy values, right? So we can, for instance, invert a random number before getting it, right? So we had a random number, then we just went from x to minus x. So now when we evaluate this computation, we'll get the inverse, right? The negated number. And the same is for read and print. If you look at the signatures, you will see that they match those of the bind function, right? That's the magic value, that's the function you apply to it, and you get an IO of unit again. So you can just do that, and this small piece of code returns the lazy computation that, once evaluated, will first ask the user for some input, and then we'll print it out. And that's just how you compose those, right? But like any mnemonic functions using bind. And so your main program will have the type of your last effectful computation in I/O. In fact, it's a really nice analogy here that what your program does, what your pure program does, it just aligns those dominoes, which are deferred computations in I/O. And when your program is run, you first get the final computation, all of those functions bound together, and you just push them. And then it runs and has all the side effects. All the network communication, all the database, read and write, all the console, input, output, random number generation, and all other effects, wanted or unwanted. But with this model, it's type safe, and your program still consists only of pure functions, which are, again, easy to test, easy to compose, easy to refactor. Yeah, basically that's what I just said, written in type. A few other advantages of this abstraction is that, okay, you can still reuse all your code. You can just use it in I/O, right? By the same way as you use your code with any other functor or monad. And then you can still have the type, part of your program which runs in I/O with all the effects. And then if one of your functions returns something in I/O, that means that you have to deal with it, because you can't unwrap I/O. You can only add more functions on top of it, right? And that's good because you will know from your type signature where you have side effects in your program and where not, eventually. And finally, you can separate, if we go quickly to, yeah, just go back to the, well, anyway, you can separate, imagine you have I/O here instead of array, right? So you can still separate your pure code without side effects, and then just lift it into I/O by using map, right? So you can modularize this part, write it only with pure functions, and test it. And then just in one small module, you can just lift it into I/O. You will still have pure functions, but you will have I/O confined to a small part of your code. Okay. And there is a state monad as well, which allows us to model state, because, well, all the programs have state, but I don't think I have time for that, unfortunately. Unfortunately for... but basically, it's the same. I mean, state operations are dynamic. You just return a tuple, right? A pair of values of some type and some state type. State type can be some record or an object or a really complicated data structure. and you want to update your state, right? You go from S to new S, and then this first type in the pair is like a side effect type. So a good example, a classic example of that is pop and push for an array. You start with an array, and then you get the new array when you pop the value, right, with this value removed, and you get this element. And for push, when you push into an array, you get new array, and then you get the new length of the array. Well, this in JavaScript works like that. So that's how it can be modeled with that. And then those functions are monadic, and then can be bound with a simple, well, not so simple actually, with a few colorful arrows, you know, that go from colorful circles. You can bind those state modifying functions together and into one function. There are more monads, or like standard monads, for instance. You see, like this model where you defer computations, like we saw in lazy and IO, and state computations, where you encode computations in state. It can also be taken into the continuation passing style, where you do, well, callbacks for your asynchronous computations. And those are monadic as well. So you can link your async code together into one piece that, once all evaluated, will provide some result. And then there are a few other monads, which I won't really talk about to save time. Finally, you can just use those monads with your types, because each monad supports all the types, all the simple types you have, int, strings, and stuff. But in languages, in purely functional languages such as Haskell or PureScript, you also have monad transformers, which allow you to combine monads into new monads. So, for instance, here, you have the state transformer and the exception transformer. So basically, that's a huge type here that describes a computation that modifies some state, right, producing some values alongside. State has this state type, that's the data structure of our state, right? And this computation can fail, and the error is encoded by the error type, which has all your errors listed. And finally, this computation may have side effects, which is signified by the usage of IO there. And wrapped into all this monstrosity is the simple value of A, which can be any type again. And because this is a monad again, it can be combined with some other monads to form even more complicated monads, and so on and so forth, all the way to infinity. So your buffet is actually, it has infinite number of dishes. Just one small demo. It's really nice, but I'll come back to it. Because let me summarize first, and then I would like to answer the questions, if any. So, if you kind of lost track of the or fabula here, then here's the takeaway. Types can be created based on other types, just like a constructor. So you can compose more and more complex types eventually to define more and more complex computations, and your functions are transformed as well alongside. So you don't have to write new code when you go to more complex types. You just have to lift your functions into this complex context. And this kind of approach allows you to write using pure functions only. Well, the advantages are clear and have been mentioned. And finally, this is kind of the purely functional approach, allows you to deconstruct all those complex types and apply, let's say, predicate logic and formally prove the correctness of your program. So you can run something at compile time, and it will analyze all the types, all the wrappings will be unwrapped, all the pills will be unpilled, and it will say, oh, okay, so this program is valid for any input, right? Because you can do it with pure functions. You can verify that whatever you put in the arguments, it will always produce the result for which this criteria are honored. And there is very complicated software for that, and written by people with like 5 PhDs each. And well, that's all with my buffet for now. I'll go back to the demo, but yeah, let's hear your questions. Thank you.
Anything at all?
So, any questions? Actually, if you enjoy this talk, we're exploring hiring Haskell and full JavaScript developers.
Well, we hire JavaScript developers.
Full JavaScript.
And then we'll make Haskell developers out of them.
For us, for one last question.
Thank you.
First of all, thanks for the presentation. I have only one question. Where can I find your presentation?
As you might have seen, I've been making the last slides in like just before my talk. So right now it's only on my laptop and I think on Andrea's laptop, but I will upload it, make it available on GitHub, I think. And then how can we share links with
We
the...
send follow-up email.
Okay,
or
perfect.
with
So it will be in this follow-up email then. You know, if you're interested in functional programming, I could also tell you more where you can read about any specific subjects mentioned here.
Thank you.
Thanks. Okay, so
Let's continue with game.
just like 3 minutes.
Okay. Just 3 minutes.
Okay. So for 3 minutes, I'm gonna show you this article. Can you see it properly? No, I didn't want to copy and paste it into my presentation because it's not fair. Basically, it shows you the difference between our Haskell and JavaScript, and what kind of monads are what makes this difference possible. So, real quickly, like that's what you get if you have lots of nullable values in JavaScript. You have to just keep checking for nulls. And there is currently a stage 1 proposal to ECMAScript for Elvis operator, just like in CoffeeScript, where you can do this. You can just, well, reduce this to a very nice looking code. But in Haskell and PureScript, you have this do notation that works for every monad, which is basically a syntax sugar for bind. So you just compose your functions with maybe, just like this. Right? It looks like just like imperative code. So that's for maybe. Then when you iterate over nested data, you use, well, nested for. I mean, what else? And then some languages like Python have list comprehensions, right, that allow you to, well, use the syntax construct to just make it nicer. But then again, you have the list or array monad. And you can use the same do notation here and bind to do that, and it still looks nice. And then the callback hell, right? Well, callback hell was really, they tried solving callback hell with so many stuff in JavaScript, just so it doesn't look like this. So for instance, you have async and await, which makes the code real nice again, but again, it's a separate syntax construct. Whereas, yeah, you also have promises, that's for sure. So 2 of them, huh? But you have continuation monad. That again allows you to write the same functions in the same way, the same type without any extra syntax, just by using the existing syntax and the fact that continuation is a monad. And finally, you have state, which I kind of told you about, right? And again, you can guess that instead of using it imperatively, like update this, update, change that, update that, you can use the state monad and still write the same freaking code. Yeah. So that was that. Oh, basically that's one nice little tidbit. It's the assembly monad, which is kind of, it encodes the assembly language in a monad. So you can write as if you're writing assembler program, because
15 seconds.
with stack and registers and all of that just by defining a fancy monet for that. And using do notation for imperative-like style. That's all I got. Thank you very much. Actually, I'll just pull the plug for now.